So when Steve Strogatz put out a note requesting that some locals give a presentation, I gladly offered to do so. I want to thank you for coming this afternoon. We'll try to give you basically an overview of work done in my group here, and as funded by NSF and ONR. And there's a number of contributors to this, but this would be a big list. So I'll thank two of the guys, without that meaning that the contribution of others is also greatly important, and I will acknowledge them all in the end. So most of the stuff you'll see here will be work by Sumit, and also strong contribution to my friend Chi, who's sitting in the back. They've both been like really brilliant people to work with, and there's also some other fantastic guys in the group that I will acknowledge as we move along. So what I'll try to keep you awake about during the next 50 minutes is I'll give you some motivation as to why I'm interested in what I do. The basic numerical method in 2 dimensions, I will try to give, again, the fundamental idea. This is all about solving PDEs as applied to simulating the equations of fluid motion. I'll talk about our existing Navier Stokes solver and some applications that we've worked on. You will not see any theorems, any proofs. First half will just be a lot of pretty pictures that are generated by this code, but these are actually very accurately generated pictures that involved a lot of care in being produced. Okay? And the second 1/3 of the talk, the final 1/3 of the talk, we'll talk about the latest generation numerical tool we've built recently in our code, which has been a real trail of tears. A lot of credit goes to Sumit for contributing here. It has to do with an efficient solver of the Navier Stokes of the pressure Poisson equation when simulating the Navier Stokes equations themselves. All right. So I'll give a summary. Slash is missing. Future outlook to wrap things up. All right. So I am fascinated by water. I grew up by the Mediterranean. It's a beautiful place, and I came to a lake. From salt to fresh water. Fascinated by both. The common thing is that below the surface, all right, I'm fascinated with what goes on below the surface. I like looking at the surface, but I like to imagine what sits below it. And this little cartoon that I show in most presentations involves here a vertical profile of density in a fairly deep ocean, but this will apply also to more coastal regions of the ocean and lakes. And you're seeing this distinct sort of gradient structure. It's fairly well mixed at the top due to storms, waves, other effects. It's strongly stratified in regions called a pycnocline or a thermocline, depending if you're thinking of density or temperature. Let's think density right now. And the position of this changes seasonally, and so does its thickness. And below it is a more weakly stratified layer. In this bottom here could be at 4 kilometers. It could be up to like 50 meters. In the shallower cases I look at, the bottom's located at about 50 meters. All right. And on the right, you have the actual gradient of the density, and it's given when multiplied by the gravity in some background reference density, standard 100 kilograms per meter cubed, 1,000 kilograms per meter cubed. This gives you the square of a characteristic frequency of the fluid. All right, so this is the gradient of the density, and it peaks at the pycnocline. And pretty much what this physically represents is if I take in that stratified water, have a parcel of water, I displace it a little bit, it'll bob around its original position with a frequency n. It's the natural frequency of my system. That said, neglecting nonlinear effects and neglecting any viscous damping of that motion. All right? So it's a measure of the strength of the stratification, and it's a measure of this natural frequency of oscillation. The key thing about stratification is that if you have a turbulent burst, all right, like you feel in an airplane, for instance, you're more experienced, but you see turbulence everywhere. There's a lot of it outside right now. When there's turbulence bobbing around in space, the stratification tends to wipe it out and restore it, typically back to some sort of laminar, quiet kind of motion. All right? That's not always true, though, and it's one thing we've managed to explore. So we're fascinated by this region here for multiple reasons. One is it acts as sort of the communicator between the surface of the ocean and the lake and the deeper waters. All right? It's stable, so it represses the turbulence, it suppresses it. Turbulence is a mixture. I'll show some cartoons to give you a better idea. It's what's going to transport energy, momentum, heat, pollutants, contaminants, biogeochemical matter from the top to the bottom. So for any turbulence to be able to do that through the stabilizing effect of stratification, you want the turbulence to be strong, powerful enough. And one measure of that is what I call a Reynolds number. We'll talk about that a little more in a second. So we care about little turbulent bursts in this region. There's also waves that ride, kind of ducted in the horizontal, and centered, most energetic right here. You can think of this as being an interface in a sense. There's very strong interfacial waves in the form of an internal tsunami, if you might call it, known as internal solitary waves. All right? Then the other thing is stratified down here too, you have wave energy bouncing around in the form of what are called beams. All right, so there's very focused energy pathways of actual gravity waves in stratified fluid bouncing up and down, and they manage to move energy over very long distances. So we care about the turbulence because it mixes through the stratified region. Stratification in general blocks stuff. So you need some powerful turbulent bursts to mix and drive stuff in a vertical direction. And you also care about energy transport over long distances in the horizontal or along these beams, long meaning of the order of kilometers by these waves. And I'm fascinated by these physics, and I want to simulate them numerically. Right? So here's a movie of what I mean by a turbulent burst. All right? This is a canonical cartoon. During the lunch, one of the students asked me, where does this turbulence originate from? It basically has to do with shear in a water column. But that, for me, that is typically vertical velocity gradients, all right? Or occurring because of the fact that I have counter-opposing currents. We might have shear at the bottom boundary, all right, because the fluid glues at the bottom. I have what's called a turbulent boundary layer there. I have these wave patterns that actually are some distribution of velocity that moves through space and has shear as well associated with it. These patterns of velocity gradients are often inherently unstable. You perturb it a little bit, and the nice organized structure like two counterflowing currents that you have right here will just go off into something a lot more complex. So right now, there's two currents going like this, or it might be the other way, but they're equal and opposite. All right, this is a very classical instability that drives this. It's called the Kelvin-Helmholtz instability. And I'm coloring stuff, and I've also got, in the top current, there's pretty much hot and light fluid. Here it's cold and heavy fluid, and I'm showing the contours of temperature in this original countercurrent configuration. And what happens is you put in a little bit of noise, and this type of situation is not stable, and it happens a whole bunch in all sorts of applications, from industry to the natural environment. In nature, at least in water, you see this a lot in what we call the middle of the water column, away from the surface and away from the bottom. Right, so I'll run this little movie, and it's been given to me by Professor Bill Smythe at Oregon State. You watch this immediately evolve. It cannot stay stable. So the current breaks down to primary instability that has a certain wavelength right here. It's initially two-dimensional. These are called Kelvin-Helmholtz billows. They roll up. Then there's a more high-order instability, like a secondary one, you might call it the next level one, which is going to appear in 1 second. Right here, you're seeing a very distinct wavelength forming over here, and the interior is starting to break down into more complex and higher order motions. All right, what happens in the end, I'll let this thing run. Oops, I want to go back a second. Let's just let it run again. Go, all right. So the reason this is important is that it's operating in a stratified environment, and eventually it's going to be suppressed and layered out. But in the meantime, it's moving stuff from top to bottom and bottom to top in a vertical, and it's mixing out the water. All right, a marine biologist cares about this. Someone who's doing larger scale, like ocean circulation prediction or any kind of weather prediction models, cares about how these little turbulent bursts modify the vertical structure of temperature, density, salinity, or anything else, let's say, in a water or a lake or even the atmosphere, at least in terms of temperature. All right, the key thing here is you've had a bunch of like a large scale motion in terms of these billows. Let me just rewind it a little bit. And there's a range of scales in this flow. I'm bring it over here. All right, so let's pause it. There's some larger scale motions, intermediate scale little whirls, and then very, very tiny ones as well. All right, so this is like a multi-scale phenomenon, to use the buzzword that everyone likes to fire around these days. It's of interest to you to capture at least the larger scales, because this is what drives what's called the steering, so it moves stuff over long distances. Then the tiny scales where it really mixes stuff in the end. We want to be able to capture, often in a geophysical situation, we have the scenario where we have a fairly large scale of about 10 meters, and then the tiniest guys are of the order of a millimeter. All right, so you've got a scale separation of the order of about 1,000. All right, and that's very difficult to do numerically. Okay, and to measure that scale separation is a parameter that I will call a Reynolds number. All right, so these little turbulent bursts can occur in isolation in some cases, but they also occur in conjunction with wave motions like this. So what is this? This is off the coast of Oregon. We're looking at about 30 meters from the water column. This is 20 meters below the surface, and there's about another 100 meters below here. And what's happened is you have what's called an acoustic echo sounder. It sends out these sound waves and off various particulate matter, which is zooplankton, phytoplankton, other creatures. You can basically sense various flow patterns that are going through here. You're seeing two things. One is a very long wave, which is about 5 kilometers in wavelength. This is the pycnocline, as I said. This is this layer of strong stratification that intervenes between the free surface and the bottom. It pushes it down, It's about 500 meters long, and the amplitude of this perturbation is about 30 meters or 40, 50 meters. And typically, this disturbance of how it takes this layer and shoots it down is about the order of, I'd say, 10 to 30% of the total water column depth. This is a very nonlinear kind of wave. And what it does in this case, it's going from left to right, and typically it maintains its form. All right, so it's a very nonlinear wave, but also the nonlinearity does not force the wave to break down, at least in terms of the core structure. It's also what's called non-hydrostatic. And in the interior now, you have this shear that I talked about. The shear is unstable, and you're getting these little turbulent bursts, sort of similar to what we showed before, what I call Kelvin-Helmholtz billows riding within the wave. Yes, sir?
What's generated the wave? The passage of a ship? Or?
No. What's generated the wave is typically you have an internal tide, the same way you have it like a surface tide. And typically what happens is, here's the coast. This is about 40 kilometers out. You have what's called the shelf break. So the topography goes from 100 meter depth to about 500 meters or a kilometer. The tide goes over like this, and it sloshes back and produces a train of waves that comes through the coast. There's other mechanisms to generate it, but this is the main one. In a lake, you have it as the wind that blows on a lake, and it forces this weird bobbing, and you get these same kind of waves. Any other questions?
Wave speed? Just roughly.
Wave speed typically about a meter per second. Meter per second in depth about 150 meter deep water. So you want to think of, if you're a fluid mechanics person, wave Reynolds numbers of the order of 10 to the 7th, 10 to the 8th. All right. So the thing is, you have very large waves that propagate over long distances. When they don't break down, these waves do not lose their energy, so they propagate in a non-dissipative manner. They're also non-dispersive in a sense that they maintain their form, and you don't get a lot of the smaller waves running away from them. All right. The waves are much larger in scale than the actual turbulent bursts that happen between them. So you have a scale separation. The turbulent bursts are localized within the wave. All right. And often this propagation is not happening in water that's of uniform depth. The depth of the ocean or the lake is changing as well. So you have what we call variable bathymetry. All right. You want to be able to simulate all these kind of physical effects. And in practice also, if you want to get to a high enough Reynolds number, all right, so that means, high Reynolds number means when you take the large scale, these large scale motions right here, they say they're about 5 or 10 meters, you're going to have smallest motions of about 1 millimeter. You cannot capture that full range of scale given your computational resources, all right? Because that means you need a lot of degrees of freedom, a lot of grid points in your simulation to get it. So you have to sacrifice the smaller scales, and you're encountered with what's called an under-resolved simulation to at least get the higher, the larger scales somewhat more physically. All right, so I'm fascinated by simulating these things. And what we want to do is pretty much, sort of the holy grail right here, is to simulate the evolution of one of these waves. All right, so this is one of these waves in what's called the South China Sea. The U.S. Navy is really crazy about these things because their submarines go through there and the Chinese submarines go through there as well. And if you're in a sub and you get caught into one of these, your life is not good, okay? So you start from out here at about 600 meter deep water, and you propagate by about 45 kilometers. 600 meters become 200 meters, and what they've done is the wave is going from, let's say, deep to shallow water. The ship goes and zigzags across it, and you have successive snapshots of the same wave. And the fact that bathymetry is changing, the depth is changing, this is called a shoaling bathymetry. And the process you want to study is the shoaling of one of these waves that are highly nonlinear or internal solitary waves. So if you want to do that computationally, you need some kind of grid like this. Things are not really drawn perfectly to scale, but you've got some starting region, and you start moving upward, the depth changes, you pack more resolution in here, and you go into deeper waters like this, into shallower waters like this, all right? So you have to account for variable bathymetry. It's not, Olivier Desjardins gave a talk here last year. The variability of the bathymetry is not as dramatic as some of the geometries you deal with in mechanical engineering devices, but you still want to be able to account for this fairly accurately, all right? And what you're showing here, these are actually not grid points, all right? So this is a 2D transect. These are actual what we call computational subdomains or elements. Each one of these is a little element with its own set of grid points inside of it. So if I blow up this region right here, I will show you the full grid now. This is just the outline of the elements interfaces themselves. This is the full grid, all right? And I try to outline the element interfaces in red. These are actual grid lines inside here. It's a little hard to see here, but it'll be obvious in some next example. The grid spacing is non-uniform for sure, so it becomes a little more packed close to the interfaces. Another thing you're seeing is that these elements right here are not square, they have a very high aspect ratio. All right, so if you do a numerical simulation, especially in incompressible flow simulations where you have these elements, computational elements that are not 1-to-1 aspect ratio, but are more 1-to-10 or 1-to-20, this reduces issues of what are called numerical conditioning, and it's very hard to solve the equations accordingly. So we want to have this element-based type of technique. So if you've done finite elements, this might be a little familiar to you. But you don't want to have linear bilinear or like second-order elements. You want to have higher-order interpolating polynomials inside these things. You want to do simulations where the numerical method will not produce a strong artificial mixing or dispersion. So your smallest resolved scales will not going to get smeared out artificially. And also any wave propagation is going to be done in a physically faithful way. All right, and this is the complexity I talked about. And of course, if we're not going to get the full range of scales in a problem, because we want to go to this high enough Reynolds number to get some meaningful turbulence, we want our simulation to be fairly stable. And this is another issue that's going to absorb about the final third of the talk, is that you want to look at physics that are non-hydrostatic. And I'll describe this in a little more detail in a second. Non-hydrostatic physics means you have to solve for the pressure equation. All right, and if you're an applied mathematician and you see the pressure equation, you understand immediately this is a very ill-behaved kind of beast, and there's people that have dedicated careers or PhDs into this topic. Okay, so what is here is we have to solve some PDEs to understand these phenomena. We could be looking at two-dimensional wave propagation. We could be looking at what are called 2D instabilities, like the initial roll-up that I showed. Ultimately, if we want to look at turbulence, we also want to do three-dimensional simulations. What I'm showing here are the governing equations in a 2D context, because this could be immediately extrapolated to 3D without a problem. The color of the projector is a little odd here, but what I'm trying to say is, here are my governing equations for incompressible flow. These are the incompressible Navier Stokes equations. Some of you are very familiar, some not, right? These are the incompressible Navier Stokes equations operating in a density gradient. So there's some kind of background density, 1,000 kilograms per meter cube of water. There's a gradient lying over it, over which the values of the change of the gradient over the depth that I'm interested in is not dramatic, maybe 5%. So I would go here from 1,000 to about, let's say, 1,002 over 10 meters of water or something. And then I have these little disturbances denoted by rho prime that are caused either by the internal waves or the turbulent bursts themselves. All right. Key thing is, if you're a mechanical engineer and you're working with reacting flows, you're looking at density differences of the order of 500 or 700. We look at density differences of like 10% at best. All right, so our equations become a little different. So here are the equations for momentum. This is the horizontal component. This is the vertical component. Here is what this equation is. The incompressibility constraint results from conservation of mass. It's not a dynamical equation. It's a constraint that enforces incompressibility. And here's an equation for what's called the density disturbance. So if you're a numerical modeler, right, one thing you got to understand is that for most cases, we cannot solve these with standard analytical approaches unless we have a very idealized problem and we want to see do some perturbation expansion or do some very basic linear stability analysis. We want to solve the full beast. All right, so here is the nonlinear term. This is responsible for all those very tiny little wiggles that you saw in the movie. All right, so the first movie, the billow rolls up and there's all little tiny motions inside the big vortex. All this comes from here. You'd be fairly evil, because it's constantly producing scales that are getting smaller and smaller and smaller, and in some cases will try to be smaller than your actual grid resolution. All right, here's the viscous term. This is the most innocuous, least dangerous one in blue. All it does is it damps out fine scale gradients. This fellow here is the restoring gravity force in a vertical direction. So when you get a density perturbation like this, it'll want to bring back whatever layer. So if you have a layer of fluid and you just shoot it up like this, it'll want to come back to where it was. And here's the pressure gradient term. All right, you could neglect this in a vertical under the assumption that vertical accelerations are not strong. This is called the hydrostatic approximation. It's used a lot in large-scale lake or ocean or atmospheric modeling to try to understand, big motions over thousands of kilometers in the atmosphere, over hundreds of kilometers in the ocean. If you have turbulence or these kind of nonlinear internal waves, the vertical accelerations are very strong, and the motions are what we call non-hydrostatic. I cannot neglect this term, and then what happens is I've got a coupling through the pressure of the two equations. In mathematics, what I have to do is I have to solve a Poisson equation, and that makes your life miserable, okay? And I want to spend a little bit of time on how this was done, especially when we want to use higher order methods, okay? So, just to give you some cartoon images before I start going to the actual mathematical model. Here's a little laboratory plume, right? You've got some difference in temperature, maybe at a source, and it's dyed hot fluid that's shooting upward. And here's the same thing with a volcano. All right, classical course question will be, how can you recognize whether an explosion in a movie is done in a studio or is a real explosion? All right. Main difference here is between these two images is what? Large scale features can be somewhat comparable, but how is this one different? Does anyone want to tell me? The one on the right? What is the basic difference that you see?
A lot of small scale
Right?
stuff.
A lot more small scale motion, so the separation between the tiniest scale and the largest one, the outline of this thing, is much bigger, so I have what's called a higher Reynolds number. All right. Now, I can simulate this on modern day computer fairly well, and I can capture the full range of scales. This is called the direct numerical simulation. But sometimes it's not dynamically that interesting because from largest to small scale, the separation is not that big. Viscosity wipes it out fairly efficiently. You can't learn a lot about nonlinear physics. Nonlinear physics typically needs large scale separation. All right? So you'll make a compromise and you'll say, maybe I won't get to this Reynolds number in Mount St. Helens, but I'll do a little volcano in the, I don't know, in a Cornell courtyard or something, an engineering courtyard. But I won't get the tiniest scales. I will not capture them, all right? So I will not capture the very small scales where typically viscosity is most efficient at wiping out energy and diffusing it. I won't resolve them. And I have to make all sorts of assumptions as to what I do about that. I can leave that for the end of the talk. The key point is if I under-resolved, what happens because of this term right here? If you're not resolving the tiniest scales of the flow, the smallest scales your grid sees, you're going to try to push energy towards the small beyond what's called the numerical cutoff, the resolution cutoff. That energy bounces back or is aliased onto your resolved scales, and your calculation blows up. All right, so you want your computation cannot see the small stuff, but it's still trying to transfer energy to it. And you have to find some way to damp it without affecting the accuracy of the larger scales. And this is called an aliasing kind of effect, this transfer from smallest resolved scales to the tiniest ones. All right, it's a real issue. Now, the other thing is this non-hydrostatic thing. All right, here are these nonlinear internal waves. So this is an actual field measurement in South China Sea. This is horizontal velocity, this is vertical. There's a wave moving from right to left. It's Paul asked. Speed of wave phase speed is about 2 meters per second. 600 meters deep water. These are about 1 kilometer long waves. You're seeing these are the isodensity surfaces. It's actually stratified water. The wave pushes it down and it carries with it this disturbance in the horizontal velocity and this disturbance in the vertical. There's strong vertical velocities, and the issue behind that is that you cannot neglect the nonlinear term pretty much in the, I made a mistake here actually. When you do what's called the hydrostatic type of approximation, you get rid of this term right here, which is the nonlinear accelerations in a vertical. That can be done for certain applications, but not when studying these things right here because the vertical accelerations are very powerful. So these are very non-hydrostatic waves. And the other thing to pay attention to is that these domains have a fairly high aspect ratio. They're relatively shallow in the context of the total length we want to explore. We often want to follow this wave for at least 10 or 20 wavelengths. All right? So hold on to this term, high aspect ratio computational domains. Okay? And turbulence itself is very non-hydrostatic as well. Waves and turbulence is what we're interested in the interior of the water. So we want to study this stuff numerically. What are the methods that we use? Okay? So here's the basic idea. In one dimension at least, right? So if I'm just solving along one line, I lay out a computational grid. How I choose my points is a whole other story. And I say that my solution will be approximated by some interpolating polynomial of higher order. It could be your standard Lagrange interpolating polynomial, which is called a nodal form. Or it could be some kind of spectral expansion where here you have a certain hierarchy of basis functions. Most of you are hopefully familiar with Fourier type of basis functions. We could have Chebyshev or Legendre, and what are called the modal coefficients. This requires information from all grid points to be set up. So it's global in a sense. In that regard, because one point is dependent on all the points throughout the grid, or at least within the grid of what's called an element, it's a lot more accurate than your standard second-order finite differences that rely on a very local interpolation concept. All right? You could take this idea and now apply it not just over your entire domain, but divide it up in elements. So what you have is in each element, there's an interpolating polynomial, and you have various coupling conditions across the element that enforce continuity of the function itself, and in some cases, continuity of its derivative. So this is a compromise. It's not as high accuracy as a full global spectral approach, but it's better than lower finite element or finite volume or finite difference. And of course, you have the flexibility then of adjusting the size of your elements depending on whether you have a very local, very fine feature. So let's say over here at the boundary there's a lot of action going on. We put a lot of small elements. I'll make them bigger as I move away. Okay? So we do this, of course, in 2D and 3D. And we wanted to apply these techniques to turbulence and wave modeling and stratified flows in a natural environment. And the technique we developed was designed to be used in what are called under-resolved simulations. So if I have a turbulent flow, for those of you that are more on the fluid mechanics side, I want to do a large eddy simulation, I will not get the finest scales, all right? Because these methods, these higher order methods, they do not produce artificial numerical dissipation, which means smoothing out the finest resolved scales, they're a lot more susceptible to these aliasing problems. So the energy that is trying to be transferred to the not resolved small scales bounces back, it kills you. So a way to do this more stably is in a context of what are called penalty methods. All right. So what you do is you divide up your domain. This is an idealized domain with just like say 4 of these elements. You divide it up in elements or subdomains as I call them. And here you have the local grid in each subdomain. Notice again how the points are positioned closer to the edge for these higher order interpolating polynomials. And you've got an equation that applies inside each one of them. And then you have to couple across somehow so information can be exchanged across the subdomain interfaces and to also apply boundary conditions. All right? So what you do is, instead of saying at the interfaces, I will have just either some communication condition, what I will do is I will have, at the interior, I'm going to have the actual equation right here, left-hand side equals right-hand side. And at the interfaces, I'm going to have the equation combined with what's called the penalty term. So in a sense, I have a smoother transition linked to the dynamics of the interior that are driven by the equation itself to the actual interface or boundary dynamics to what's called a penalty term. All right, so you're not just applying strongly a boundary condition or an interface patching condition, a boundary condition at the boundary or a patching condition at the interface. You're using this penalty kind of approach, and this provides for greater numerical stability. And I can explain to you why later on after the talk. All right. You have what's called a spectral filter and the aliasing technique. These are basically ways to give even greater stability. And the interpolation and discretization is based on what's called a collocation method using Legendre polynomials. For the beginning, we're just going to use these Legendre polynomials in subdomains only in a vertical and a horizontal. I'm going to have a Fourier type of technique. All right? So the idea here is you have an equation at the interior of your subdomains. And then at the interface, you have the equation collocated with what's called a penalty term. The penalty coefficients are computed based on some very basic energy analysis of the linearized equations when you discretize them. I won't go into the details of that. All right. So let's say you want to use this to solve the incompressible Navier Stokes equations. All right. The 3 terms that trouble you are the advective term, the nonlinear one, the viscous term, and the pressure term. How do you apply this idea? So let's say if I can formulate things for linear advection, I can do it also for nonlinear advection as well. So here's my standard linear advection equation. This is what holds at the interior of the subdomains. Here's the penalty term. Basically all this means is there's a penalty coefficient obtained on this energetic stability analysis grounds with what would be the advective flux at the actual subdomain interfaces. So I have a term like this, the stuff that's flowing into my subdomain. If it's flowing out, I don't put anything. All right, so this is a general idea. Equation plus penalty term. It's an advective flux type term for your advection. All right. If you've done finite volume type of analyses, you might recognize this to some extent. All right, this is the type of viscous operator, diffusive operator that we encounter. Fairly innocuous, but what happens is the structure of this interior penalty term is a little different. All right, if you're looking at the boundaries of your domain, this is adjusted to match your boundary condition. By the way, epsilon is the viscosity of the fluid. You basically have an operator like this. Where this originates from is a little blurry, but it's basically telling you that you're forcing some requirement, a condition for the variable itself, velocity or density, and the normal gradient at the interface of the variable. All right? And last but not least is the setup of the pressure equation. I won't go into the details of this too much, but this is the equation you end up solving for, all right? So you have Navier Stokes, and you want to advance from level n to n plus 1. what we typically do is we apply an operator splitting technique. All right, so as we go to this level, if I want to go from here to n, 10 plus 1, I will take 3 intermediate steps. I will first deal with my advective operator, which I just showed. Then I'll take care of the pressure. Then I will use the pressure to update my velocity to make it incompressible. And then I have to do one more intermediate step to take care of my viscous term, where I will pretty much enforce my velocity boundary conditions. This intermediate step for the pressure is one of the toughest ones to deal with in terms of numerical linear algebra and actual computation. Here's what the equation typically looks like. It's a Poisson equation, which comes by taking the divergence of the actual momentum equations. And the penalty term can have varying structures. In the interior, it's a little similar to what you do for the viscous term. For the boundary conditions, it looks a little funkier. The key issue right here, this is a Poisson equation with a Neumann boundary condition along the boundaries, all right? So you apply some value. This is the gradient of the pressure normal to your boundaries, all right? So if you've got an equation like this, equipoise a boundary condition is a very ill-posed kind of problem. And when you want to do it numerically, it can cause you a lot of grief. Okay? So this is the idea behind the penalty method. And what we did is, initially, well, this is the code I developed during my postdoc, we said we want to look at flow in a box. All right? Not very complex geometry, but the physics is complicated enough. So think of a 3D box. All right, in a horizontal direction, I'm going to assume it's periodic, so I'm going to use a Fourier type of discretization. You're hopefully familiar with Fourier polynomials in the applied math world. And because often in environmental flows, things get localized in a vertical, either near the surface, at the center of the domain, is this example right here. This is showing a cut through the box, and you're seeing the interfaces of the subdomains. All right, you're using the subdomain approach only in one direction now, only in a vertical. All right, and you can localize stuff anywhere in the water column, or the center right here, or at the bottom. Okay, and you can use what's called a rigid lid approach. You're going to assume that your top surface is not deformable. All right, so just a flat lid. Flow cannot go through it, but flow can slide onto it. Right, this is what the oceanographers call a rigid lid. Mathematically, what this means is by virtue of continuity, you do not solve a pressure Poisson equation. All right. Typically, what you do is you transform stuff into Fourier space in the horizontal direction, and you solve a bunch of one-dimensional problems. You avoid this equation, which is the devil in this case. All right. This is what we developed, and we applied it to a whole bunch of problems. I'm going to show some little examples right here to hopefully illustrate, the flexibility of this technique. And the first thing, let's see, I want to say is a little bit about parallelizing it, all right? So before I go to the examples, we simulate flow in a box, all right? And this is a 3D box, and what you do is, if you're sitting in what we call physical space, so in the y and x direction, you have not before you transform your data, you have these vertical slabs right here of certain thickness, and you cut the domain in slabs like this. Each processor, all right, so you're applying this to a certain number of processors, 4 in this example, gets one of these slabs. All right. Once you do that, you have to often Fourier transform your data, which is the biggest source of cost here. You isolate one of these slabs, and you have to do a whole data transposition to make the slabs from being aligned in the x direction to being aligned in the spanwise coming out of the paper. All right. So sort of data transposition is one of the biggest challenges for MPI type of programming, and it's often what causes the bottleneck. Moreover, the number of processors is typically limited by the smallest number of grid points in either of the horizontal directions. So for those of you that are more parallel computing oriented, we're trying to hybridize this code to take it from pure MPI to what's called OpenMP/MPI to use like a mixed distributed and shared memory kind of paradigm. So what you would do ultimately is also break up one of these slabs into smaller entities in a vertical to solve things faster. It's a little bit beyond the point of this talk. So what if we use this for? And a little bit about the actual pressure solver in the next 15 to 20 minutes. Here's the classical example to motivate this. I'm giving credit to Chi because he's done tons of work on this problem. You've got your little 3D box. You've assumed the sphere is shot through here, and it's left behind it a wake of water. All right, who's interested in this? Especially when your water is stratified. But, in the thermal climate, the technical climate of the ocean, when we're stratified, it's not spheres that move through very high velocities. It's other objects that are self-propelled and are basically Navy run. Okay? Moreover, so this is a submarine wake, but you can also understand wakes of underwater mountains in this regard. From the point of view of oceanography, you care about the turbulence behind the mountain and how it mixes the water and redistributes all these biogeochemical constituents we talked about. The toy problem considers a sphere. it's gone through here, and then a little bit after the passage of the sphere, you assume an initial conditions, a stratified fluid, and you watch this wake evolve. Okay? The canonical idea is that, sphere is shot through here, you're just watching this little wake evolve. It's stratified water. Stratification effects, as we said, damp the turbulence. So what it should normally produce is a very damp, sort of slow-moving motion with very little vertical turbulence, almost none at all. In the end, what you get are what are called pancake vortices. So what's left is sphere shot through here. It's just very little vertical motion, almost nothing. And you see these little spheres, these little eddies that are called pancake eddies, just rolling around, rotating with very strong vertical vorticity, so spin in a vertical direction. And that should happen very rapidly. And what these numerical simulations enable to do, the fact that we use a high accuracy technique like this, was that to show that maybe this is not the case. So here's a very beautiful movie she put together. Just focusing on this side right here. These are simulations of a stratified wake of a towed sphere. Okay? And I'll bring it back to the beginning in a little bit, but if the sphere's shot through me this way, we're showing a horizontal plane right to the center line of the wake. And this is the vorticity of the fluid coming out of the paper. This is this plane. I'm rotating up. It's the horizontal midplane of the simulation. All right? So they all start out looking pretty turbulent once the sphere's gone through here. But this is what's called the low Reynolds number. All right? Laboratory, Reynolds number 20 times higher. We managed to push it by about a factor of 4 even further. The actual geophysical case is about a factor of 200 even higher. The key thing you want to observe is that whereas at these times, at the laboratory case, it's this very nice, smooth-looking pattern, you're getting a lot more fine-scale structure as you move up in Reynolds number. That was against the common perception of a lot of people that would think that you could only get this case here with these very smooth eddies in a real ocean. Why does that happen? It has to do with the fact that you get these very, very fine layers. If you take, this is now a vertical plane, so if your sphere's gone through here like this, you're sitting here in a vertical, you get very, very, very fine layers as you increase the Reynolds number. These are very prone to going unstable and producing secondary and further turbulence. A standard numerical method cannot capture these that accurately. The issue here, of course, is that these are fairly expensive simulations, almost up to 1 billion grid points. The cost is huge. The number of the size of the data set is also gigantic. So it's one of the challenges here is that there's a non-trivial aspect in terms of performing the high-performance computing type of studies and dealing with the data and waiting for it as well. Yes?
What are the boundary conditions of this problem?
What are the boundary conditions? This is a 3D box, okay? Let me just go back here. It's a 3D box. It's periodic in this direction, all right? It's periodic in this one, so the box is wide enough so you don't have interaction with the periodic images. There's theoretically another box sitting right here, another one, another one, another one. It's wide enough, and then in a vertical, you have typically what are called free slip conditions, like rigid lids. So everything's far away. There's also wave radiation and other problems that are quite interesting as well. Yes?
And you've solved the problem of the sphere moving through the box already, right? We're just looking at...
Yeah, so you assume the sphere shot through here and it's left behind some velocity distribution.
Well, how do you establish your initial condition?
That's like a 5-minute discussion.
Oh, okay.
I can tell you later.
But they don't arise from a computation you do. They arise from a...
The lab experiments cannot get such detail close enough to the sphere, and computations are barely getting there, but they're at really low Reynolds numbers. So we have to make some assumptions about it. So the very initial phase is not super reliable. It's not physically exact, but eventually it adjusts, and you match the lab measurements. So another little problem, big problem, is this is again one of these internal solitary waves. So there's a little density gradient. There's 2 layers here. Light fluid, heavy fluid. There's a density gradient between them. And here you have one of these long waves. It's producing this depression that I showed earlier. And what happens is this thing is going from right to left. It pretty much acts like a vacuum pump on the bottom, right? And it produces very strong pressure gradients, which in 2 dimensions produce instabilities in the boundary layer of vorticity. So this is the spin of the fluid coming out this way. This is the vorticity. You have what's called the boundary layer separation effect. And you get these little vortices that are bouncing off the bottom. These are awfully similar to the type of vortices you might have noticed. If you've seen this image of a flow over an airfoil, flow goes over it through the curvature of the airfoil, you get shedding of vortices that bounce off, right? Similar mechanism, totally different type of aspect ratios and length scales, right? This is a wave that could be about a kilometer long, in 100 meter deep water is quite different. We try to do this in actual simulation now in 3D. All right, so now you add another span-wise direction. These are the sizes of your grids. All right, all credit goes to former postdoc Tak Sakai. The transition to turbulence, all right, to watch this thing in 2 dimensions, once you add a third one, go turbulent, is incredibly complex. I'll just show some pictures of what the turbulence looks like by the proper visualization tool in different positions along the grid. It's extremely interesting. It's also a very difficult calculation to do. There's similar group work done by Mahmoud for similar transitions from instability to turbulence under what are called surface solitary waves. Unfortunately, we don't have much time to go there. But here's an image, right? So initially, this is an indicator of a vortex. And you see these little vortices that are somewhat dislocated. Your wave is sitting somewhere. So here, this is sort of a tracker of where you sit with respect to the wave as you track along the bottom. Your wave's right here. You're moving down this way. And suddenly, once you go to this position, about 1 wavelength away from it, you're getting the first transition in 2D instabilities for these various dislocated type of vortices. It breaks down what's called the transitional structure further down. These are called hairpin or lambda vortices. And eventually this turns into a really big and ugly mess further and further as you go away. So this little wave, this huge wave, as it propagates under the bottom, is producing these really messy kind of turbulent structures that are pretty much resuspending stuff from the bottom into the water. All right. We've been able to attack this, but this is really pushing the edge of available computational tools. So to finish the tour of duty here for the existing tools, it's not just turbulence that you look at, it's also wave propagation problems. All right. This is a model for what's called an internal tidal beam. Often in the interior of the ocean, you have what's called an internal tide. So you have some bump like an underwater mountain, and a flow just oscillates over it, the stratified flow. As it oscillates, you get various type of structures that leave away from the underwater mountain. And often you get these little beam-like structures that come up towards the top of the surface, and they encounter again this infamous pycnocline, and what happens there is they break down and all sorts of other effects tend to happen. And what we focused on is what's called harmonic generation. All right, so these are fairly finite amplitude waves in the stratification. You're looking at the same metric that is used in a laboratory to measure these things. This is pretty much a measure of the local vertical density gradient. These are waves that are coming upward. They hit the surface. They hit what's called the pycnocline. The surface is up here. It's not stratified. That's why you don't see anything right here. This is what's called the base of the mixed layer. All right, the base of this well-mixed region. And some stuff bounces down. Then energy also gets ducted into here, and you have some very interesting nonlinear energy transfers. It's of interest to oceanographers because you get a better idea of how energy is redistributed inside the actual water. All right. So this is the type of problems we looked at so far. And all these problems, going back to Vasili's question, in a horizontal, my boundary conditions are always going to be periodic. And I can use this trick of what's called the sponge layer that can absorb energy at the edges. But I'm periodic here and here. My span-wise, I'm also periodic. In a vertical, I use this multi-domain approach. I can have arbitrary boundary conditions. So I can put whatever boundary condition I want. I can also focus these little elements wherever the action is. And the goal was to try to extend this approach to another direction. All right, so can I also put non-periodic boundary conditions right here? And can I actually allow for variability in my bottom bathymetry? All right, so my bottom boundary is not just going to be a nice flat one, can actually deform it. And that's going to be what I want to spend the last 15 minutes of the talk on. So there's a variety of other problems we looked at. I'm listing all down here. I'm giving credit to the people that have worked on it. But let's go to this new type of code. All right, so now my box is not going to be periodic in one of the horizontal directions. It'll be non-periodic in a vertical, non-periodic in the X. All right, sounds trivial, but it's not easy to implement. Now your elements are no longer just these little, they're not just linear ones, just in a vertical, they're little squares in a horizontal direction. Like if I want to go back really quick, where are we? I have to worry about elements of this type that will also be deformed as well. Okay? So what are the concerns that pop up? You typically now have linear systems with much larger matrices that are non-symmetric. If any of you have taken Dr. Van Loon's classes or Dr. Bindel's classes, you know that if you have a symmetric matrix, the arsenal of tools to solve linear systems of equations is incredibly more flexible and powerful. The other thing is the matrices are large, so the question is, do you solve the systems iteratively or directly? And you typically want to follow the route of an iterative method. But for one equation that's not going to work, you're actually going to have to do it directly. We got to that conclusion after about 5 years of effort, maybe 6. And what's that equation? It's the pressure equation, okay? As I said, if I want to advance from time n to n plus 1, I have to pretty much deal with each operator in the equation separately. First, I take care of the nonlinear advection, then there's the pressure, then there's the viscous terms. For the pressure, in the end, I have to solve an equation that looks like this. There's a right-hand side here that has information that links from the contribution of the nonlinear terms, and there's this type of boundary condition right here that tells you at the boundaries, the normal gradient of the pressure is what is prescribed. This is not that well behaved. In fact, the analytical solution is an infinite number of solutions because you have an additive factor that is undetermined, okay? And then when you want to go and think about this in terms of the discretized system of equations in the actual matrix, you have pretty much a non-zero null space, right? A singular matrix. Moreover, this equation here should be subject to what's called the compatibility condition. If you take the right-hand side and you do the integral over the whole domain, this should match the actual line integral along the boundaries of my boundary condition. These problems that we work on, the flow simulation problems, are extremely complex, all right? This G here originates from the contribution of the nonlinear term. The nonlinear term is what generates all the very fine scale motion you see in the fluid. It also produces numerical noise at very subtle levels. So what happens is this compatibility condition between the boundary condition and the right-hand side is almost never satisfied. So in a linear algebra standpoint, it produces a linear system that is pretty much inconsistent. You cannot solve it. You have to take care of that. Now, if you want to look at the oceanographic problems, you also want to have this variable deformed bottom. All right? That's going to make your life even more difficult. Already dedicated a whole PhD to these iterative method solvers. And Sumit came along. He made a drastic change of direction to go to direct solvers for the system. I'm going to spend about 10 minutes speaking of his work. He's done a fantastic job. I'm grateful to him for his patience and his focus. It's a non-trivial problem to deal with. All right? And you want to solve this equation because you want to capture what are called these non-hydrostatic dynamics associated with waves and turbulence, and you want to study them in domains that are long, okay, and shallow, and also have a variable type of bottom. If you don't want to look at those physics, maybe you're in a better position, but you're also limited as to what you can look at. All right, so what is this pressure Poisson equation that I indicate by PPE? You apply this whole multi-domain penalty type of scheme, and you produce a linear system that looks like this. So L is just the matrix that results from discretization of my operator. B is my right-hand side vector that comes from discretization of assembling the right-hand side on a grid. All right. So we said a compatibility condition is not matched, and in a linear algebra sense, what that means is that there's no solution for the system as it is. All right. It's inconsistent. So the typical approach to this is to regularize the right-hand side in this fashion right here, and you bring in this weird little vector called U naught, which is the left null singular vector of this guy right here. All right. So if you've taken Dr. Van Loon's class or some of the other classes available in matrix computation, this is a non-symmetric matrix. You cannot do an eigenvalue decomposition for it, eigendecomposition, but you can do what's called a singular value decomposition that you may have heard of before. And you care about pretty much the matrix of the left singular vectors. And you care about the one that corresponds to the 0 singular value. Computing this is not a trivial process. If your matrix are symmetric, this is just a nice vector with constant entries. Your life's a piece of cake. We have non-symmetric matrices that originated from this collocation idea, and it's a challenge to get this. If your domains are not deformed, they're just nice little squares or rectangles, you can appeal to the structure of the matrix and use various what are called Kronecker product ideas, where pretty much you can take a 1D discretization in the x direction, a 1D and a z. You can combine all this together, and if you know the 1D corresponding null singular vectors by doing a Kronecker product, you can build this, and you can do this, what's called the regularization of the right-hand side. When you deform your domains, you can't do that, and you often have to appeal to what are called iterative solvers. You may have heard of RPAC, some form of inverse power iteration, if you've heard that in your numerical linear algebra classes. So a little bit of discussion on what this matrix is about. All right, so here's a toy domain. It's got 4 elements in each direction. Sitting over here are the actual element interfaces. depending on how you decide to index your points, all right, because what most folks do in finite element world is they index locally in each subdomain. So start at 1, 2, 3, 4, 5, 6 here, 7, 8, 9, 10. Depending on how you index this, you will generate your Poisson, the sparsity patterns is called for your particular Poisson matrix. All right. So this here is the matrix that comes from discretizing that Laplacian operator based on a penalty scheme that we talked about. Okay. What Sumit decided to do is a slightly different indexing scheme, but what's important here is the structure of the matrix that pops up. All right. So you have these very, very little tiny blocks in the interior that have to do with the role of the x derivative, and here are these big blocks. He's got 4 of them. Pretty much each one of these blocks corresponds to this first strip of points. So the first element in horizontal, all the elements in it in a vertical. Second element is this block. Third element here generates this block. Fourth on. All right. So it's got a block structure, and that is fairly tempting to you. Nonetheless, the matrix is non-symmetric, and because of the higher order polynomials, it's pretty much almost singular. If you're going to deform your elements, what's going to happen is these little white spaces in here, they will also get filled up. All right. So you want to exploit that structure somehow to build a fast solver. When we had just undeformed elements, we built an iterative solution technique with what are called preconditioners, special matrices that will reduce the condition number of the matrix but retain its properties. It worked decently. It had a lot of problems in these very long domains that we wanted to look at from a geophysical perspective. We eventually aborted it because it did nothing for actual domains with deformed elements. Okay? And the number of points, if you're just doing like a 2D simulation of this wave propagation, is the order of about 10 million. So your matrices size is pretty much 10 million by about 10 million. They're huge, okay? But you can play games to store this fairly efficiently, exploiting sparsity patterns, and also by decomposing your domain accordingly and applying some sort of parallel domain decomposition approach. So this is what you do. And this is where Sumit has been brilliant. You take these cuts, all right? Typically our domain maybe has 5 to 10 elements in a vertical, because this is, the depth of the water. But I can have about 1,000 of these little subdomains shooting all the way down that direction. So you cut it up in slabs, all right? Each one of these slabs corresponds to one of these blocks right here. And this domain decomposition is used, the decomposition is used from the point of numerical linear algebra, but it's also used from a parallel computing standpoint when you want to apply this mixed MPI, OpenMP kind of hybrid approach. So what you do is each project gets one of these slabs, and then you can work, if you're sitting on if you've done parallel computing, you have one node that has multiple cores. These work on this in an OpenMP kind of context. Now, setting the parallel computing aside, what you do is you break up the matrix like this, and using this color scheme here, you have these blocks these just have contributions of what's called the derivative operator, just the equation, right? So this is the contribution of the Laplacian itself in each one of these slabs. And you have these little red elements. That's what's called the communication or patching condition at the interface between subdomains. All right. So what you do is you recognize that pretty much you can write your matrix like this. It's pretty much the sum of all these little block-like matrices. So A here has these 4 contributions in this example. And here you got these other little matrices right here. Okay? So there's a matrix B that contains these red entries right here. And there's some repositioning matrix E that puts them in the right spot in the sort of global matrix structure. All right? So this was identified because an iterative method was not working for us, and we lost years and years and years. Now, your goal here is when you want to solve a linear system, which is like L times X equals B, you want to be able to invert L in a certain sense using some numerical linear algebra tool. You can do that by building what's called the Sherman Morrison Woodbury kind of identity. All right, so about another 5 minutes of esoteric math, and then we're going to end the story. So these are these individual matrices. So A was all the little big blue blocks. B are these little red streaks right here. This is the matrix that will take all these fellows here and reposition them in the right spot. Okay? Now, if you know that your matrix can be written in this type of structure right here, there's an actual formula that will give you explicitly the inverse of L minus 1. All right? So your pressure will pretty much be L minus 1 multiplied by B. So this is what you're looking for. So X is your unknown, this is the pressure you're trying to solve for. You have this explicit formula, where you've exploited the structure of the matrix, regardless of whether your subdomains are nice squares or deformed, and it looks like this. All right. Key point is that pretty much you have an A inverse. A, remember, is the contribution of each one of these blocks multiplying B, and you have this little thing also. A inverse is operating from here onto B, from here onto B, and there's all this other stuff hanging out right here. Of the other stuff is this matrix C right here, that's known as the capacitance matrix. All right, so this has worked wonders for our system, even though in practice your Poisson matrix and what's called the capacitance matrix are not invertible. The key thing is A inverse times B is very easy to do in parallel because you just isolate one of these blocks. The blocks here, if you forget about the red part, are not coupled across each other, so it's easy to invert this in parallel. And then you got to worry about this capacitance matrix, which it's hard to identify associated meaning with it, but it's much smaller in size than your matrix L when you're using what's called the high order method. All right, and I'll talk about that in a second. So it's smaller in size by pretty much a scaling factor, which is 1 over n. It is the number of points. We typically work with about 10 points in each direction. So it's a number of points in each direction. This is about a factor of 10 smaller. It has much better conditioning properties. And if you remember this infamous little regularization that we did, so we have to adapt the right-hand side to account for the lack of solvability of the linear system. We can work with our matrix C, which is much easier to manipulate to get its own left null singular vector, and from that we can generate the left null singular vector of the original Poisson matrix. All right, and this here uses some special iterative package known as RPack. So here's the sequence of steps that you use to solve this Poisson equation. A lot of math here, but the key thing to hold on to is you first take care of these products. You invert your A in a very easy parallel fashion. So then you take care of the role of the blocks. Then you got to take care of the role of the capacitance matrix. So you solve two different systems. A inverse is done with a direct type of solver, all right, for each one of the blocks. And then the actual coupling operator is taken care of in the context of the capacitance matrix, which uses an iterative method. So then what you do is you've inverted the blocks, and you got to take care of the role of the actual coupling rows in a matrix, your matrix B, and you assemble everything back together. This here, the capacitance matrix is solved for in an iterative fashion. It's fairly fast, and you do not need any preconditioner. And this is what these slides were supposed to say. I'm going to skip past it. I'm going to say that it's much faster than using an iterative method. And what I want to do is just bring you, like actually showing you a little picture right here. In two different examples, this is what this has been able to do before I end the talk. So this is what's called the stratified lock exchange. So you've got, there's a gate here, virtual gate. You've got heavy fluid, light fluid. You pull the gate, the heavy fluid slides under, the light fluid slides over, and here along this interface, there's shear. And you get instabilities that form, all right? It's a 2D simulation, and often what this is called is a gravity current. Unfortunately, the subdomain interfaces are not popping up here, but you've got about, I believe, about 20 subdomains in the vertical and maybe 400 in the x direction. And you're getting this pattern to form very, very nicely without any numerical instabilities, without having excessive resolution. And if you're a numerical person, the key thing you want to worry about is that the density values that are generated do not lie outside the minimum set by the minimum by the heavier, set by the density of the heavier fluid, and that of the lighter fluid, which is the maximum. So it has very good conservation properties. And here's just a little animation of this. Evolved a whole sequence of instabilities, done in a very, very reliable way as compared to various other numerical methods. And I'll show just one little picture in the end as we wrap this up. Okay, so these are these Kelvin-Helmholtz billows that I talked about earlier on. It does it in a very, very robust and very accurate kind of fashion. We've actually applied this to a number of very basic benchmarks that involve analytical solutions or different types of solutions with like more higher accuracy kind of methods. So I want to come back to this one other little image. This should not be here. Oops. Where are we? This is the last application that I'd like to show. This is, oops, here we go. So this is what's called the shoaling of a nonlinear, an internal solitary wave. It's the problem we ultimately would like to study. So you have like a sort of uniform depth region right here, is the depth here is changing in almost in a linear fashion. I could add some curvature to this. It does happen. The key thing is this is successive snapshots of a wave that started over here and shot down into shallower water. All right, this is density. I've got about 100 meter deep water right here and a length of a domain that is about of the order of 15 to 20 kilometers. All right, this is what you actually observe in the field. A low order accuracy method will produce a wave that will break down due to numerical dispersion. It will actually spread out artificially due to numerical diffusion. The key thing is that the wave retains the structure very well, and it's simply all it does is it opens out in amplitude according to the prediction of theory, simply because the waveguide is getting deeper, shallower, and you have to redistribute the potential energy of the system. So we're trying to fine-tune this a little further to allow for more deformable geometry in the bottom. It's just more of a pretty straightforward exercise, and we want to add a third direction to be able to account for actual turbulence, at least for some range of scales. So in summary, the code that I just showed that we developed originally is a box. You can use this multi-domain approach in a vertical. It can look at fairly complex physics, at fairly high Reynolds numbers and simple geometries. We're working on various speed-up aspects of it because we're really trying to push the edge of computation. If you want to do a simulation that involves element approaches in one more horizontal direction, your biggest challenge is the pressure Poisson equation. If you have these elements to be deformed, it gets even tougher. And it all originates from the fact that your matrix is non-symmetric. Your linear system is non-solvable, so you have to account for it by computing this left null singular vector and adjusting the right-hand side. Iterative techniques do not work, at least for this problem, when having deformed subdomains. So what Sumit has done in a wonderful way is use the Sherman Woodbury Morrison identity to build a very efficient direct solver that exploits the sparsity pattern of the matrix. So we're still applying this to a number of other benchmarks and writing things up. We do want to add a third spanwise direction that is periodic. This is very easy to do compared to all the other stuff we've had to do here. And ultimately, we want to include what's called particle tracking, so you can track clouds of particles that account for either bottom sediment or biological material in the water. Sumit's working to make some connection with underwater acoustics, and the holy grail is to actually see how these motions affect bed morphodynamics, to have another whole other domain beneath that allows for not just deformed bottoms, but time-dependent deformation of these bottoms. All right, so I've bombarded you with a lot of info, so I'll leave you with a little picture right here. And I will thank a bunch of other people that have contributed to this kind of development. All right, so thanks, and I'm open to any questions if you have the energy.
Why can the spectral methods deal with so much higher Reynolds number than direct numerical simulation?
But the ones not preclude the other. So direct numerical simulation means that you're capturing the full range of scales. You can do that with a spectral method. You can do that with a lower order method. If your domain is fairly simple, you want to go the route of a spectral technique because the idea is you get more of a bang for your buck. So let's say higher Reynolds number means a more complex signal, right? So it's got large scale variations to very tiny scale variations. To represent your signals on a given grid, you need to make a choice of interpolating function. If you're going to use a low order technique, you're using some kind of Taylor interpolant that's very local, or maybe at best second order. You need a lot more points to represent that complex signal with a low order interpolant technique, which is the basis of finite elements, finite differences, finite volumes, versus a more global or element-based global technique that you use for spectral. So if I need, let's say, 1,000 points in each direction to capture the full range of scales at a certain Reynolds number, if I need 1,000 points with finite difference, with spectral I might need 100. So therefore, I can use those 1,000 points with the spectral method to push the complexity even further and push the Reynolds number a little more. And then I'm also at the mercy of what computers I have available.
And why do you need fewer for spectral?
Because the interpolating polynomials are incredibly more accurate. That's one thing. And then
I mean, you're using them all simultaneously.
in a global sense, yeah, that all points are connected. That brings other issues into play, though. The other thing that a spectral method is much better is that there's not what's called numerical dissipation built into the schemes, or it's tiny. So there's not some sort of underlying process that's diffusing out your signal at the smallest resolved scales. You might have to include some dissipation in the context of a spectral filter to keep things stable, but that's more focused and more controlled. So that's our claim to fame at least. But we can't do any of the simulations that Olivier's group does because his geometries are wicked complex. We'll say that. So I think that's my answer there.
Oh, I think we're a bit out of time, so maybe let's stay and repeat again. And if you have any other questions, you can ask me.
Thanks.
Thank you.